So I have uploaded the manual. So for the first experiment will be realization of modes, the fiber modes. So we will see the propagation of LP01 modes. So you can see that first we have to design the core and cladding of the optical fiber. So the core and cladding, we have to mention the dimensions of the diameter of the fiber and wavelength and refractive index. So this is the software. You can see that RSoft. Initially it was RSoft. Nowadays Synopsys has taken. Synopsys software, it is very well-known software. Synopsys has taken over this software, but it is old version, so RSoft is coming here, and it is very useful software for the design of optical fiber. Many fiber optic components can be designed using this. So basically, in the lab, two softwares are there. One is related to design of fiber based devices. Okay, that is optical fiber based devices like fiber, any kind of fiber. Then coupler, okay, coupler 1:2 coupler or any 1:to multiple n coupler. Okay, so and you can design some modulator also. Do you know that the modulator, what is the role of modulator, is that when we use very high frequency signal, let us say gigahertz, so you cannot modulate the light source, okay, like LED or laser, using that frequency because the electronics is not available. The transistor will fail at that frequency. So you need to use some optical devices. So that will be used for modulating the optical carrier, okay, like wavelength or any wavelength, using with modulation of optical carrier with some applied signal. So that is another experiment. So first we will see the design of optical fiber, simple optical fiber, and next experiment will be design of Manchester electro-optic modulator. Electro-optic modulator. So first, this is, you have to press the new circuit button. Then you see there are several parameters coming, like waveguide dimension is 3D. You have to select. Then wavelength, you have to select 1.55 micrometer. You can change it. Then background refractive index. It is the cladding refractive index. The setting is such that in software this represents the cladding refractive index N2. N2 is 1.45. And index difference delta is given, that is 0.01. 0.01 means it is the index difference. You know that N1 minus N2 by N1. Okay, that is the difference between the refractive index, the core and cladding, divided by the core refractive index. So from once if you define these two parameter into and delta, then you can easily get the values of n1. So after that, you have to mention the waveguide width and height. The waveguide that will draw or design will take this dimension automatically. 3 and 3 means 3 micrometer in diameter. Okay, and height and width are same in case of core, your circular core fiber. If they are different height and weight, then they are called elliptical core fiber. The normal regular fiber is having circular core. Then you will see that profile you have to select step index profile. There are a lot of profiles available: step index, Gaussian. This kind Gaussian is used for graded index fiber design. Diffused, since some portion there is change in different layer, or any new profile you can design it. The next is the 3D structure type. 3D structure type is you have to select fiber. So once you design it, then once you set the parameter, then you press OK button. After pressing OK button, you see this window opens, and here is the cursor. We keep it at this axis. There are vertical axis and another is horizontal axis. So it has some origin point 0, 0. So I will drag some region, I'll design some region, and if you just drag and drop. So from the origin I will design it. Okay. And I will leave at some places. You can leave it at any place. So this red portion is actually the fiber core region. Fiber core region, and this dotted region is the cladding region. Okay. So this fiber design is over. Core is the red region. After that, you have to select the light source. Light source means is light launching. So you have to press this button, light launching, and then you have to keep the options for Gaussian, because any field is launch field, so launch field is generally Gaussian. Then you press OK. Only this thing you have to change, Gaussian. Then after setting the light source, next part is you have to monitor the light propagation. So for that, you have to click Edit Pathways. Edit Pathways, then New. Then so once you click New, then the waveguide region into which you want to see the light propagation, you have to click it. So it becomes green. Okay. So the core portion I have selected because I want to see the light propagation in the core region. Then here you have to press monitors. Monitors I have pressed. Then you have to select a monitor that will show the design designates the mode. Okay. See, you see that it is fiber mode is coming, fiber mode power. Then you see that here 0 and 1. That is azimuthal angle. LP new M. So new is 0 and 1 is M. That is the order of the Bessel function. Okay. So you know that mode is nothing but the solution of that is solution of Maxwell equations with different electric and magnetic field orientations. So each mode is designated by the propagation vector beta, and beta is nu m, designated as nu m. Okay, so this nu m is 0, 1. Then you see that, then you press OK. So if you do this, that means you will be able to see the propagation of LP01 mode. LP01 mode, then I press OK. Then I keep it here, then press OK. Then I will run, perform simulation. देखिए ये फिर ऑफ हो गया, रन नहीं कर रहा है. अभी बीच में तो बताने जा रहा है, अभी रजिस्टर बीच में था ना, वो बीच प्रोसेस में था, ये रिस्टार्ट करके आइए सर्वर को. हमेशा देखते रहना है चालू है कि नहीं. You just wait for few minutes. अच्छा उस कंप्यूटर में हो जाएगा ना? ये तरफ फैन को ऑन कर दीजिए थे ये वाला। Okay, now we have what we have demonstrated that ये तरफ फैन ऑन कर दीजिए। So after designing the core, okay, here what we do that we have to select the launch field, edit launch field, then what we have done in Gaussian mode. Okay. Gaussian mode, then okay. So then again going to monitor, then new, then select the waveguide region, and then again monitors, then new, fiber mode power, and 0 1 for LP01. If you keep it 1 1, then this should be 1. Okay. Then okay. So after that, you have to perform simulation. पेन लेके आइए। हाँ ठीक है एक पेपर पेन लेके आइए तो पेपर लाइए तो। So now you see that the mode is propagating. Light is propagating this way. So all of you just take the snapshot of it. You see that some Gaussian waveform is propagating, that is actually LP01. And it has one peak. It has one peak. Okay, it is propagating now. And at the side window, you see that straight line. Actually, this straight line actually represents the power of that particular mode. Okay, and the value of the power is at that point is it is nearly 0.335, 0.336, let us say 0.336. So note down the values for these readings that when we consider that radius, okay, radius is 3/2 micrometers. Okay. Then P core, light propagating in core is actually 0.336. Okay, 0.336. So this is this power. Now here you have to calculate the V numbers. Okay. V number is how much? Formula of V number is 2 pi by lambda into A into numerical aperture. Numerical aperture is N1 into root over 2 delta. Okay? N1 to root over 2 delta. And this N1 is actually what is the relation between N1 delta is what? Delta is N1 minus N2 by N1. Okay. So you can calculate that the value of delta, okay, and you put the values of N1 over there, or so is actually delta is equal to 1 by N2 by N1. So N2 by N1 is equal to 1 minus delta, and N1 is equal to N2 by 1 minus delta. So that means 2 pi by lambda into N2 by 1 minus delta into root over 2 delta. So you put the values of all that. N2 you have used 1.45, okay, N2 1.45, then A is 3 by 2, radius because diameter we have taken 3, so it is 1.5 micrometer, and then you calculate V numbers. So for different values of radius, you will get different values of power. So that I will show here. Now next case we consider that the core radius should be certain another value. So dimension width. The height कहाँ गया? Height and width. Height next we go for 4. 4 and now you see this is the propagation of light for next value of radius or corresponding next value of V number. Okay, so you just note down the power now. Power is increased and it is near about 0.7. Okay, 0.7. So next value is 4 by 2, that is 2 micrometers. You have to calculate V number and power is 0.7. Okay. Then you go for another value of the height and width of the fiber. That is, let us say you keep it 6. Then perform simulation. Now you see core size is increased and light is also propagating there and more wide field. Can you note down the power? Power is now how much it is? 0.95. 0.955. So next reading is 6 by 2. 6 by 2, no, 6, 6, 3 micrometer. Then you have to calculate V number and power is 0.955. Then another value consider of this, that is, let us say slightly higher value, that is say 10 micrometer diameter, and you see light power propagation is almost reach to 1. Okay, 0.99, 0.98. It is 10 by 2, that is 5 micrometers. You have to calculate V number, and it is 0.99. कितना हुआ reading? 5 और then another value, let us say it is 14 to 16, say. Yeah. Come on. Okay, now so this is for the LP01 mode. Okay, so I will share these values of these readings, and you have to plot one graph like plot of V number versus power. So it will be a graph like this. So initially it is very small. Okay, then up to this it will go 1. Okay. So there are 5 points you have to plot, 4 points, this, and this. So this way you have to plot the graph. So this is for the first experiment of software. Rating what maybe. Now next experiment is Manzender interferometer. Okay. So it is already designed. Now what is the principle is that here light enters to the fiber and it is split into 2 parts, okay, in 2 arms, 2 parts, and again they meet. So if light is launched from here, then that light is divided and again meets. So at this point, there is interference. So now depending on the phase difference between these 2 lights propagating in the 2 arms, okay, output will change. Okay, you know that if the phase difference is integer multiple of 2 pi, then it is constructive interference, and if it is phase difference is multiple of pi, then it is destructive interference. So depending on the phase difference of these 2 light, the light output will change. So as I told you that if you apply some voltage here, so these electrodes are applied. Okay, you can apply electrode. So generally at one path electrode is applied, and the other path no electrode is applied. Okay, but still you can apply two different voltage. But our purpose is to keep one voltage constant at one electrode or 0 volt, and other electrode in the other arm will vary the voltage. Okay, so, and we will observe the power. So let us run here that what is the voltage now. But now it is voltage is set to 1 volt. Okay, so then for 1 volt I run the simulation. Then you see some windows have come. Okay, so that actually shows the light propagation in two arms, here and here, and this is the final light. Final light is 0 volt. Okay, you see that 0 volt is there. So now you make one table. So experiment 2 for software, that is voltage and power. Okay, so for 1 volt we get 0 power. First reading, then second reading is, then again we change voltage there. So let us say I keep it to 2 volt. Okay, and then again perform simulation. So now you see the voltage is increased. Okay, that is highest value. Okay, so 1. So for 2 volt, the power is almost coming to be 0.9, 0.94. So one shows very low power, another shows very high power. So you have to take very small voltage increments. Okay, so let's start from very small value. So we started with 1. Now let us say we start with from 1.5 volt, 1.25 volt. So for 1.25 volt, लिखिए तो, for 1.25 volt power is 0.16, 0.155, 0.16, 0.16 0.16. The next value of voltage, that is 1.5 volt. Now light output is generally now 0.47, 0.47. The next reading is 1.75. So for 1.75 output voltage is 0.8, 0.79, 0.79, 0.79. Then another reading 2 volt already shown. Okay. So after getting these results, you have to plot one graph. Okay. So this graph will This graph will be like a sinusoidal one. So I have taken, say, let us say from 1 to 1.1 to 2. Within this range, it is actually this way it is increasing. Okay. Sinusoidal it is increasing. Okay. So you have to plot this one. Okay. So for other readings also, I will give you slightly few readings. Okay, so let us keep it for 2 volt, 2.25. So for 2.25 reading is 0.81. नीचे लिख दीजिए 2.25 2.25 में 0.81 0.81 ही है ना ये एक से 0.81 then 2.5 0.5 2.5 0.5 then 2.75 is 0.18 0.18 2.75 0.18 and 3 volt लिख दीजिए 3 volt करके लिख दीजिए 3 volt it is almost 0.02. Okay. So one cycle data for one cycle I have given you. Okay. Half cycle I have given you. So you have to plot it. I will share the file. Okay. So this is about the second experiment of the software, that is Mach Zehnder electro-optic modulator. Okay. This can be used as sensor also in case of fiber. So in case of this is actually for electro-optic modulator, lithium niobate material is used, not fiber. The lithium niobate material. It has the property that if you apply any electrical voltage, its refractive index changes. So refractive index changes in one arm, so phase will change in one arm only. So phase difference will change between two light, and accordingly the output will be generated. So this is used for modulation of optical signal or any wavelength with the input electrical voltage. Okay. And it may be used as fiber also, optical fiber sensor. This is very high sensitive sensor. And in place of this waveguide or lithium niobate crystal, optical fiber is used. Okay. So their principle is same. If you apply some force, the refractive index gets changed in one arm and causing the phase change of light in that particular arm. So phase difference between two light will change, and accordingly interference will occur, and resulting variety of different amplitudes of light for different values of applied physical parameters like strain, temperature, whatever it is. So it is very versatile device. Mach Zehnder modulator. Okay. Now we'll move to the another experiment, third experiment. Okay, that is actually we have to go to that lab. Okay. The manual लिखा है ये। So now you see another software is there that is called OptiSystem. Okay. So here, so in Manchester, so this OptiSystem software is actually used for simulating or designing a fiber optic system. Okay. Any fiber optic system. So it may be optical communication system, any optical particular device. So here we have used that software to design one technique for coding, one coding technique, that is Manchester coding technique. So you know that in hardware you have seen Manchester coding. So generally at the mid bit position, okay, at the mid bit position there is bit transition according to the input data. If it is 1, then it goes from high to low. If it is 0, then it goes from 0 to 1. So those things is implemented and transmitted through optical fiber. So for that, what components are required? That is one light source, okay, and many components like XOR gate, light source, light detector, receiver circuit, etc. So yeah, it is given in the manual. So I am showing you exactly from the diagram that the data sequence is generated using this pattern. Okay, any data sequence you can generate. So just by double clicking it, you can. No, actually, it is initially totally blank screen. Okay. Now you have to place. So by searching, find component. So here you write sequence generator. So many components you can plug and play. So we have used here the data sequence generator. Okay. So this data sequence generator it is actually one code. So that is converted into one channel coding, that is energy pulse. Then that binary code another used for clock signal generation. That is alternation of 0, 1, 0, 1, 0 kind of thing. Okay, and it is this sequence we have considered as the binary data whose Manchester coding will be performed. Okay. 10101011 like that. 10101011. Then we use XOR gate. So once they are actually electrical data, they are converted into XOR gate. Then that output of the XOR gate is applied to a modulator LED circuit. You can design, you can use any light source. It is actually laser light source. You can see the frequency of the laser, that is 193 terahertz. 1552 nanometers. 1552 nanometers. So let us keep it to terahertz mode. Then press OK. Then it is used passed through the optical fiber. Then 1 kilometer optical fiber you see. It is a 1 kilometer optical fiber we have used. It may be of any value. Okay. Any length can be used here, can be put here. And then after that, receiver circuit is there, optical receiver. Basically, it is a photo detector. So you have this photodiode, that is spin photodiode. Spin photodiode and avalanche photodiode, two options are there, spin or avalanche. Then after that, we see the detected light. It is in analog form, so you have to convert it into digital form. So for that, you have to use threshold voltage or AMRE threshold detector. So either AMRE or single level detection is sufficient. Then you have to apply for the D flip-flop. So now let us see the waveform.